In our last lecture, we discussed the principle of operation of a fully controlled bridge, in which all the 4 switching elements are thyristors. We derived the expression for average value of output voltage, and it is given by 2 Vm by pi into cos alpha. This expression is valid if the current is continuous. I will repeat, this expression is valid only if the load current is continuous. We found that for alpha in between 0 to pi by 2, average value of the output voltage is positive. Current is unidirectional, so power supplied by the source to the load is positive. So we call it as conversion, AC to DC converter. And for alpha greater than pi by 2, we found that average value of the output voltage becomes negative. Current is again unidirectional, which is positive. So power supplied by the source is negative. In other words, source is absorbing power, load is supplying power back to the source. So we call this as inverter or inversion, power inversion. Average value of the output voltage can be negative for alpha greater than pi by 2 only if the load is of RLE type. Okay, it is possible only for RLE type of load. Motor will act like a generator only if torque developed by it is negative. In other words, torque is given by K phi into Ia. Either Ia has to reverse or E has to reverse. Polarities of E should reverse. Only by changing or only by increasing alpha greater than pi by 2, machine will not act like a generator. Okay. So for the machine to act like a generator, I have to either interchange armature terminals or I have to interchange the field terminals. Let me tell you one thing. For converter fed a DC machine, reversing the armature terminals or field terminals using the mechanical contactors doesn't make sense, because both are inductive circuits. Field circuit is highly inductive, even armature has a finite inductance. Using mechanical contactors, I have to, or to interchange the terminals, I have to use a mechanical contactors. So momentarily we are breaking an inductive circuit. So what happens if I break an inductive circuit? Arcing will take place. That's what I said, using mechanical contactors in a converter fed machine for the machine to act like a generator doesn't make much sense. Okay. So is there a solution? Is there a way out? There is. We'll see. Yeah. So this is the equivalent circuit of the fully controlled bridge. 2m by pi into cos alpha. So magnitude of this voltage varies, is a function of alpha. There are at any given time 2 thyristors are conducting, Tx and Ty. So either T1, T2 or T3, T4, and here is the load. So applied voltage to the load is equal to the output voltage of the bridge minus 2 device drops. Okay, remember 2 device drops. So if you assume that the devices are ideal, it is average value of the output voltage applied to the load is 2m by pi into cos alpha itself. Otherwise is this value minus twice or 2 device drops is the voltage applied to the load. Okay. So we used only one converter wherein voltage is reversing but the current cannot reverse. So we will use one more converter connected back to back, in the sense current can flow back to the source with through the second converter. So there are two converters, hence the name dual converter. Okay. So if you see converter 1, voltage can be positive or negative, current is always positive. So operation is in quadrant 1 or quadrant 4. Now I have connected another bridge in a reverse fashion wherein current can flow back to the source. Okay. Now negative current corresponds to, with respect to the bridge 1, the direction of current flowing in the converter 2 is in the opposite direction. So voltage again can be positive or negative. So operation is either in the quadrant 2 or in quadrant 3. So in other words, using a dual converter I can have all 4 quadrant operation. All 4 quadrant operation is possible. Okay. Okay. So here is the circuit, power circuit. Single phase bridge T1 to T4. I have and another bridge here T1 dash to T4 dash connected in the reverse fashion. Two bridges are interconnected by 2 inductors, and in the center I am connecting a load. Okay. The purpose of this inductor I will tell you sometime later. Okay. What is the principle of operation of this bridge? Assume that both the converters are working. Okay. And let alpha be the trigger angle or alpha 1 be the trigger angle for the bridge 1. Now what is the relationship between alpha 1 and the trigger angle for the bridge 2? So let it be alpha 2. Okay. So we know if the current is continuous, average value of the output voltage of the bridge 1 is given by 2 Vm by pi into cos alpha 1. Similarly for the second bridge it is 2 Vm by pi into cos alpha 2. Remember both the bridges are being supplied by the same source. What the KVL gives? Though there is an inductor, average value across this, average value of the voltage across the inductor is 0. So I have taken VO1 with respect to bus Y, with respect to this VO1, potential of this bus is VO1, and see here I have connected this bridge in a opposite direction, back to back. So T1 dash is here, T1 is here, T4 dash, T3 dash and T2 dash, and output voltage of this bridge is VO2 with respect to this bus X. So VO2. So the KVL gives VO1 plus VO2 should be 0. Okay. VO1 plus VO2 should be 0 because voltage across this plus this is 0. Okay. So it gives the relationship between alpha 2 and alpha 1 is this. The trigger angle for the bridge 2 is pi minus alpha 1. Okay. So here is the equivalent circuit, 2 Vm by pi into cos alpha 1, output voltage of the bridge 1 two devices are conducting at a time. 2 Vm by pi into cos alpha 2 is output voltage of the bridge 2. Again, two devices are conducting here. I have not shown the inductor. The load is connected in between. Now, if I plot the output voltage, average value of the output voltage with alpha 1 and alpha 2, how do they look like? For the bridge 1, it is given by this equation, 0 at pi by 2. Okay, this waveform we have already drawn for single phase fully controlled bridge. So alpha 1 is 0, so alpha 2 is pi. So magnitude is the same, it is -1. So I am calling Vm by pi is equal to 1 or 1 per unit. So similarly, therefore Vm by pi minus Vm by pi is -1 per unit. At pi by 2, both are zeros, and this is the variation. How does the now let's draw the waveforms, output waveforms. How do they look like? Okay. At alpha 1, which is less than pi by 2, G1 and G2 or T1 and T2 are triggered. G1 and G2 of the gates of T1 and T2, and at pi plus alpha 1, T3 and T4 are triggered for the bridge 1. At omega t is equal to alpha is a trigger angle, alpha 1 is a trigger angle for the bridge 1, and alpha 2 is a trigger angle for the bridge 2. So G1 and G2 are triggered in the positive half at alpha, and at pi plus alpha 1, G3 and G4 or T3 and T4 are triggered. So how does V1 look like? So till T1 and T2 are triggered, T3 and T4 were conducting. Recall whatever all these things we have studied. So prior to T1 and T2, T3 and T4 were conducting. So output voltage is negative, because from 0 to pi, VBA is negative. This is VBA and this is VAB. Okay, VBA is negative, so VO1 is negative. At alpha 1, T1 and T2 are triggered. Now the output voltage is VAB, so instantaneously there is a jump. Now output voltage is VAB, it will continue till pi plus alpha 1. At that instant T3 and T4 are triggered. Okay, this waveform we have already studied. How does VO2 look like? See, now just reverse this bridge, in the sense take this minus and plus. Okay, alpha 2 is the trigger angle for the bridge 2, and the relationship between alpha 1 and alpha 2 is alpha 2 is equal to pi minus alpha 1. Okay, so somewhere at this instant G1 dash and G2 dash, the gates corresponds to T1 dash and T2 dash are triggered. Remember, in the positive of T1 and T2 are triggered. Similarly here I am triggered similarly here T1 dash and T2 dash are triggered in the positive half. Okay, somewhere here. So till T1 dash and T2 dash are triggered, T3 dash and T4 dash were carrying current, or they were conducting. So output voltage is negative, T3, T4. So the moment T1 dash and T2 dash are triggered, output voltage is again V A B is positive. Okay. So average value, the magnitude of average value, that is magnitude of VO1 is equal to magnitude of VO2 if you find this one. Average value of VO1 may be equal to average value of VO2. Okay. Now let's see what is the voltage waveform appearing across L1, or what is the voltage waveform that comes across L1. Okay. Now VO1 is this. Now I'll reverse the polarities of VO2. So this is VO2. Now minus VO2 looks like this. The same waveform, I am inverting it. Same waveform has to be inverted. Okay. So now with respect to the bus Y, or this bus, this is VO1, and with respect to this bus, potential of this is minus VO2. Okay. What do you observe from these two waveforms? I said mod of VO1 may be equal to mod of VO2, but then instantaneous value of VO1 is not equal to instantaneous value of VO2. Remember, mod of VO1 may be equal to mod of VO2, but then instantaneous value of VO1 is not equal to the instantaneous value of VO2. So therefore, there is a potential difference between the voltage across the net. So there will be a current flowing from bridge 1 to bridge 2, or in other words, there is a circulating current. There is a circulating current. Hence the name, the circulating current type converter. Okay. So in a dual converter, if both the converters are carrying current simultaneously, they are known as circulating current type. Okay. If only one bridge is carrying current, it is known as non-circulating type, because only one bridge is carrying current, only one bridge is supplying current to the load, second bridge is completely off, so no current can flow to the second bridge, hence the name non-circulating type. Okay. So VL is nothing but VO1 minus of VO2, so here is this. You will find that average value of this waveform is 0. Okay. Now let us see how a dual converter can be used to control a DC motor. Now this load will connect a DC machine here. Okay. Let us assume that machine is running stably at some constant speed omega, and corresponding EB back EMF is of the order of 90 volts. Just assume if back EMF is 90 volts, so applied voltage, output voltage of the bridge should be higher than 90 volts, only then the current will flow. In other words, output voltage of the bridge should be equal to IA RA plus EB. So let us assume that VO1, the magnitude of VO1 is equal to the magnitude of VO2 is around 100 volts. Okay. The output voltage of the bridge is 100 volts, the magnitudes, and EB is of the order of 90 volts. So let us assume that corresponding trigger angle for the bridge 1 is around 45 degrees. So therefore alpha 2 is pi minus 45 is equal to 135. So I will repeat, alpha 1 is 45, alpha 2 is 135, corresponding VO magnitude of VO1 is 100, the magnitude of VO2 is again 100, and EB is 90. It's okay, it's possible. Now I want to feed the, you want to use the regenerative braking and reverse the speed of operation. Okay. Initially motor was running as a machine was operating as a motor and was rotating in the clockwise direction. Okay. Torque is positive, speed is also positive. Okay. Quadrant 1 operation, torque is positive, positive torque, and direction of rotation omega is again clockwise. Okay. Now what I will do is increase alpha 1 towards 90 slowly. So VO1 becomes less than EB. Okay. When I am increasing alpha 1 towards 90, simultaneously I have to do, or I have to decrease alpha of alpha 2 of the bridge 2. Okay. So I am increasing alpha 1 towards 90. Similarly, alpha 2 is decreased towards 90 of bridge 2. Now we will find that VO1 is less than EB. So if the terminal voltage is less than the back EMF, now current can, the direction of current can reverse. Okay. So now initially if the current was entering terminal A of the armature, now it will leave the terminal A. How does it flow? Now it will flow through the bridge 2. Okay. See in this direction. Initially current was flowing in this fashion. Okay. Current was flowing in this direction. This was 100 volts, 90, EB was 90. Magnitude of VO2 is also 100. See, I made it now, I will reverse the terminals here. Now I have reduced VO1 by increasing alpha 1 towards 90. So VO1 has reduced, or VO1 is less than EB. Now current can leave this terminal, so it can flow through Tx back to source. Okay. So this is the path. If this operation is known as the motoring, this is the regenerating action, or motor is acting like a generator feeding energy back to the source. Machine is feeding power back to the source, there is no mechanical input, speed falls. Okay. As the speed falls, I am also reducing VO1, or in other words, alpha 1 is approaching towards 90 degrees, alpha 2 is also approaching towards 90 degrees. Okay. Speed is falling, assume that speed is approaching 0, at that time VO1 is also approached 0 and VO2 is also approached 0. Corresponding is alpha 1 is and alpha 2 both are approximately 90 degrees. Now continue to increase alpha 1 above 90. Now what will happen? This will, VO1 will change its polarities. Now this will become minus, VO2 will become plus. Okay. VO2 will become plus. Now initially quadrant 1, now then we went to quadrant 2 operation, because speed was, though it was falling, speed was still in the same direction. Direction of rotation is the same, still in the clockwise direction. Torque has reversed because initially current entered the polarity A, current entered the terminal A. Now current is leaving terminal A, the torque is negative, so we are in the quadrant 2 operation. Power is being fed back to the source through the second bridge. Current is flowing back to the source through the second bridge. Okay, regenerative braking. Okay, so omega falls, continue to increase towards 90 degrees. At alpha 1 is equal to 90, V1 is also 0, omega approaches 0, increase alpha 1 beyond 90 degrees, alpha 2 below 90 degrees. Now bridge 1 is acting like a inverter and bridge 2 is acting like a converter. Now bridge 2 supplies power to the machine. Now machine starts rotating in the negative direction. Machine starts rotating in the negative direction. So if quadrant 1, if it is known as forward motoring, quadrant 3 is known as the reverse motoring. Okay, direction of rotation is the opposite. Now increase alpha. Alpha 1 towards 180 degrees. So therefore alpha 2 decreases towards 0, So average value of the output voltage increases, both the magnitudes are increasing, so the speed is also increasing. At steady state, machine is running in the reverse direction at some omega. Okay. Now if you want to do again regenerative braking, follow the same steps. Okay, follow the same steps. The operation goes to quadrant 4. Okay, so this is the principle of operation of dual converter fed DC motor. Okay, that's enough theory. Now let's see, let us solve one or two problems in converter fed DC motor. Okay, a very simple problem. A fully controlled bridge supplying power to a DC machine. RA is of the order of 0.3 ohms. EMF constant is of the order of 0.17 volts per RPM. Problem says that assume a large inductor is connected in armature circuit. So the moment you see the sentence, you need to assume that armature current is continuous. Okay. Determine speed and supply power factor. Okay. Alpha to the bridge 1 is, or trigger angle is maintained at 30 degrees. So what is the average value of the output voltage? Since the current is continuous, it is 2 Vm by pi into cos alpha. I am saying that current is continuous because a large inductor is connected in the armature circuit. So you can safely assume that current is continuous. So therefore, average value for alpha is equal to 30 degrees is found to be 179 volts. So V minus IARA is equal to E. So EB is of the order of 170 volts. Okay. Armature current is 30 amperes is given. Okay, it's constant, and you can assume that IA is constant and ripple free. Okay. Now how do I determine the speed? EMF constant is given. EMF constant is volts per RPM. The magnitude of EB is known. So I can calculate speed because volts per RPM into RPM is volts. So EB divided by EMF constant will give you the speed. It's found to be 1000 RPM. How do I determine the supply power factor? There are two ways. Okay. One way is we assume that armature current is constant and ripple free. So I average is 30 amperes. Okay. What is the power supplied to the load? V average into I average is power supplied to the bridge, or input power to the bridge is V average into I average. So V naught into I average is the power input. What is the input VA? It is VRMS into IRMS. VRMS is same as 230 volts because we are assuming that input is ideal sinusoid. Current is constant and ripple free and magnitude is 30 amperes. So RMS value of this current waveform is 30 amperes. Okay. We have found that if the current is constant and ripple free, each device is conducting for pi radians. If each device conducts for pi radians, RMS value is same as the average value. So IRMS is also 30 amperes here. So input VA is 230 into 30, that is 6900 VA. The V average into I average is 179 into 30 watts. So therefore power factor is power divided by volt ampere is of the, so it is found to be 0.77 and it is lagging. Remember, the moment you introduce alpha, power factor lags. Even at alpha is equal to 0, power factor is not unity. Displacement angle may be unity. Remember, displacement angle is not equal to power factor angle. So they are different. So displacement angle may be unity, sorry, displacement angle is equal to 0, in other words displacement factor may be unity, that doesn't mean that power factor is unity. Okay. So power factor is 0.77 lag. What is the second method? Second method I have already discussed. Source current is a square wave for pi radians. The fundamental component of the square wave is 4 by pi into the magnitude of the current. This is the peak value. So RMS is divided by root 2. So the RMS value of the fundamental component of the source current is 2 root 2 by pi into the current. It is a, for this case it is around 27 amperes. For a fully controlled bridge, we found that displacement angle is same as the trigger angle. In other words, phi 1 is same as alpha. So displacement factor is equal to cos of the trigger angle. It's cos of. Source current may be a square wave, so therefore it has a fundamental component and it has a higher frequency components. I told you that only the fundamental component of the input voltage and current are responsible for power transfer. The higher frequency components give rise to I square R heating or additional heating in the machine. The other effects we will see sometime later. So power transferred is V1 into I1 into cos phi 1. Okay. The fundamental component of the input voltage into fundamental component of the source current into the cos of the angle between these two waveforms divided by VRMS into IRMS. Now since input voltage is a sinusoid, fundamental component is same as the RMS component. So V1 cancels with VRMS. We found that the fundamental component for a square wave is 2 root 2 by pi into 30, where 30 is the magnitude of the current that is flowing in the load. which is assumed to be constant and ripple free. So it is about 27 amperes. Alpha is 30. So cos power factor, or sorry, power factor is given by or in this case is found to be 0.779. In both the cases they tally, and both the cases they have to give the same answer. It's up to you to choose whichever method is convenient for you. You don't need to follow the method 2 or method 1 explicitly. It's up to you. Part 2 of the problem is regenerative braking is used, but in this case problem says polarity of back EMF is reversed. See, I have not discussed this. Okay, all the time, so I have discussed reversing the armature terminals or reversing the armature current. Here the problem says back EMF, polarities of back EMF is reversed. It is possible by reversing the flux. How flux is reversed, let us not discuss. Either they would have used a dual converter, or they would have used a contactor, make and break, interchange the field terminals. Okay. So problem says calculate alpha and power fed back to the source. Armature current is maintained at the previous value. Okay. The same current of 30 amperes is flowing. So here is the equivalent circuit. Mind you, he has interchanged, the operator has interchanged the polarities of back EMF. Simultaneously, he has increased alpha greater than 90. Okay. I did tell you in the beginning of the lecture, increasing alpha alone above 90 degrees in a single converter will not ensure that the machine or motor will act like a generator. Similarly here, interchange the terminals alone will not ensure the motor to act like a generator. I have to interchange the polarities and simultaneously increase alpha above 90 degrees. Okay. So this is the equivalent circuit, current is still flowing in this direction. Prior to the polarity reversal, EB was 170 degrees. Okay. For alpha is equal to 30, we found that VO or the VIN is 179, 30 amperes is the current that is flowing, RA is 0.3 volts, so 170 is the voltage here. Okay. Now EB is minus 170, current is still flowing in this direction of 30 amperes. What is the value or what is the magnitude of V in? It should be 161 volts. Okay. IA area drop, the difference between this should be IA area drop, current is still flowing in this direction. If this is 170, this is 161. Okay. So current is continuous. Listen, current is still continuous, so therefore alpha is 141 degrees. What is the amount of, or what is the power fed back to the source? It is nothing but V in into I average. Okay. Or output power of the generator minus IA squared into RA. What is the power output of the generator? EB into IA, 170 into 30 is the output power of the generator, minus I square R losses, 270 watts, therefore power fed back is power output of the generator minus I square R losses. This should also be equal to V1 into I1 into cos of the angle between V1 and I1. Okay. Because we are assuming that converter is lossless, or in other words efficiency of the converter is 100%. Okay. Generally efficiency is very high. In all our problem solving we are neglected the device drops. Actually, the voltage applied to the load is slightly less than 2 Vm by pi into cos alpha, because two devices are conducting at a time. Okay. Yeah. If you recall, one of the assumptions that we made, in the very first lecture of converters, is that source inductance is 0. Okay. But now let us consider the effect of source inductance, because source inductance is always finite, because power is being fed through the transmission lines or underground cables. There is a transformer at one end, it has its own leakage inductance. So source inductance is finite. Now let us see the effect of source inductance. If the source inductance is 0, the moment T3 is triggered, T1 turns off, because current can instantaneously change. Okay. Okay. See, here is the waveform. IL is a constant and ripple free. Somewhere at alpha, T3 might have triggered. So when the moment you trigger T3, T1 turns off, and current reverses. At this instant T1 is triggered, T3 turns off and positive current, and here T3 is triggered, T1 is turns off, negative current. So current changes instantaneously. This is possible only if the source inductance is 0. Source inductance. Now if there is a finite source inductance, what will happen now? What will happen to the output voltage? We will see. Consider a simple case. Now I am using a center tap transformer with the T1 and T2. Let me tell you one thing, you can do this analysis for a fully controlled bridge also, similar steps. Okay. So VIN is a voltage induced in the upper half of the transformer, VBN in the lower half, L is the leakage inductance or inductance of this path. Similarly, L is the leakage inductance of the transformer, T1 and T2 are the thyristors, this is the load. At alpha 1, in the positive half, T1 is triggered, at some alpha, at pi plus alpha, T2 is triggered. Now source inductance is finite. Now how does output voltage look like? Okay. Initially the entire I0 was flowing through T1. Entire load current was flowing through T1. T2 is triggered. Now current through T1 starts decreasing. It cannot come down to 0 instantaneously because of this L. At the same time, current through T2 starts increasing. Since we assume a load current is constant and ripple free, or I0 is constant, so IT1 is equal to, or IT1 plus IT2 should be equal to I0. So IT1 decreases, IT2 increases, so that the sum remains I0. Okay. Now what the KVL gives? KVL is VIN is equal to minus VBN is Vm sin omega t. So KVL, if I use KVL, VIN minus VBN is equal to L di T1 by dt minus L di T2 by dt. So in this circuit, if I use KVL, VIN minus VBN is equal to voltage drop across this inductor and voltage drop across this inductor, KVL. Here current is decreasing, its current is increasing. Okay. So Now dit1 by dt is equal to minus of dit2 by dt. Okay, current slowly decreasing, current slowly increasing. Okay, similarly here it2t, current through this thyristor 2 is decreasing and it is increasing in the thyristor T1. Okay, and both the thyristors are conducting for a finite time, what is known as mu. Okay. Now substitute this condition in this equation, we will find that Vm sin omega t is equal to L di T1 by dt. Okay. What is VO? This voltage is nothing but VAN minus L dit1 by dt. We found that VAN is equal to L dit1 by dt during mu, so output voltage is 0 during mu. In other words, when both the thyristors are conducting, output voltage become 0 in a single phase. Okay. So in this period output voltage is 0. So prior to T1, T2 was conducting, voltage is negative, same waveform. Okay. During mu, output voltage is 0. When T2, current through T2 has become 0, in other words entire current T1 is carrying now. Okay. Now VO is nothing but VAN itself, that is Vm sin omega t, and this is the waveform. So you will find that there is a net reduction in the output voltage. If source inductance is 0, we would have got an instantaneous rise here and would have followed this way. Okay. Output voltage would have been instantaneous change and would have followed this way, but then here due to source inductance for a finite time this output voltage is 0. So from observing this waveform we can conclude that because of the source inductance there is a reduction in the output voltage. What is the magnitude of the reduction in the output voltage? We will find we will derive an expression. Okay. So here is where are the various equations? They are very simple and straightforward. At alpha to alpha plus mu, it1 is given by this equation because Vm sin omega t is equal to L dit1 by dt. So I can derive this equation use from this, integrate this, and at alpha at omega t is equal to alpha plus mu, it1 is nothing but I naught. Okay, I will repeat, when omega t is equal to alpha plus mu, this quantity is I naught itself because entire current it1 is carrying. So since both the thyristors were conducting during mu, this period is known as overlap period or overlap angle. Mu is also known as the overlap angle. Okay. Now what is the expression for the average output voltage? Because now there is a 0 voltage period during mu. From alpha to mu, average alpha to alpha plus mu, the instantaneous value of the output voltage is 0. So the expression for average V naught is 2 by 2 pi into alpha plus mu into pi plus alpha. Okay. So here is our expression from alpha plus mu to pi plus alpha, it is Vm sin omega t. Okay. It is not that alpha to pi plus alpha is it's Vm sin omega t. Now it is alpha plus mu to pi plus alpha, it is Vm sin omega t. So you will find that average V naught is given by this equation. In our previous expression, that is here cos alpha plus mu, so we will substitute for this factor and you solve it, you will get this expression. So Vm by pi into cos alpha plus mu is equal to Vm by pi into cos alpha minus I naught into omega by pi. This is from a previous equation, equation number 1. Now if I substitute this in this, I will get this equation. Now can I draw an equivalent circuit for this equation? So here is it, 2m by pi into cos alpha, which is again varying. There are two thyristors here at any given time. In this case there may be one, okay, but then if I use a bridge where two devices are conducting at a time, into omega L by pi into I naught is the voltage drop due to the source inductance. Mind you, I have represented by a resistor here, omega L by pi. So I naught is the current that is flowing through the load, so remaining is the voltage across the load, V naught. So what is our another observation? We find this from this expression that average V naught is 0 for two values of mu. One is mu is equal to pi or mu is equal to pi minus 2 alpha. For both these values, average value of V naught is 0. Now let us take first condition, mu is equal to pi. First of all, can I have that sort of a condition? In the sense, for the entire pi duration, there is a short circuit. In other words, output voltage is 0 for pi radians, both the thyristors are conducting. The entire positive half cycle is the overlap period for thyristor 1, and the remaining pi radians in the negative half is the overlap period for another thyristor. In other words, source does not supply any power to the load, but then we have assumed that load current is constant and ripple free, and there is no period, or in other words, there is source does not supply power to the load at all. How is this possible? Yeah, this is possible only if the load is an ideal current source. Remember, it's an ideal current source. Voltage, terminal voltage is independent of, or the current that is flowing is independent of the terminal voltage. Okay, voltage applied during mu to the load is 0, but then constant current is flowing. This is possible only if the load is an ideal current source. The second condition is mu is equal to pi minus 2 alpha. So let us draw the waveforms. How does it look like? At alpha, T1 is triggered. Okay, overlap period is pi minus 2 alpha. So this is mu. So this should be alpha. So this is pi minus 2 alpha. Again at alpha, in the next half, at alpha, one more thyristor is triggered, that is T2 is triggered. This is the commutation overlap period, and at this point commutation is complete. Entire current the thyristor starts carrying it. So if you see here, average value of the output voltage is 0, positive half is equal to negative half. So what sort of a load? it is an ideal inductor. So second case ideally may be possible, for that matter even the first case, if I connect a constant ideal constant current source, a single phase bridge is feeding, so mu is pi, it is possible. In the second case, if I have an ideal inductor, I can have a situation wherein overlap period is equal to pi minus 2 alpha.